Here we consider the problem, prove that every open interval contains infinitely many rational numbers. The solution is, we know that an open interval is of the form open interval a b minus infinity a b infinity or minus infinity infinity. This open interval is bounded, but others are not bounded. If we can show the result for this open interval, then for others it will be done easily, because in these three open intervals contain these types of open interval. Now here it will be sufficient to show that between a and b there exists a rational number, and we use the density property of rational numbers, that is, between two rational numbers there exists infinitely many rational numbers. Otherwise we will show the rest part independently. So we start with the relation a less than b. We have to show that between a and b there is a rational number of the form m by n. So from this relation a less than b, we will get a positive number, and this will be obtained by b minus a greater than 0. From this we can write this one. Now we use Archimedean property. For we need a positive number, so that positive number is b minus a over here, and we let it be x, and we take y as 1. Then by Archimedean property there exists a natural number n such that n times x greater than 1 y. So here x is b minus a, y is 1, so we get n times b minus a greater than 1. And from this, if we divide both sides by n and n is positive, so we'll get this one, 1 by n less than b minus a. So if we draw the sketch, we'll find that 1 by n is less than b minus a, and n is positive, 1 is positive, 1 by n is positive, so 1 by n is greater than 0. So 1 by n is in between 0 and b minus a, this one, or you can write this one from here. Now from this relation we get 1 less than nb minus na, and we write na plus 1 less than nb. This inequality is numbered as 1. Now we consider the number na. So what is the motivation of this consideration? So look back at this relation. Here we get on the left na less than m less than nb. We have to show this one. So na over here. So we consider this number na over here. Now n is a real number. It may be positive, 0 or negative. Now we use a deduction of Archimedean property, and there exists an integer m such that m minus 1 is equal to na less than m. So from this relation we get m less equal to na plus 1, and na plus 1 is less than nb from 1, and from this relation we get na less than m, na less than m. Now from this and this we'll get the relation na less than m, na less than m, and m is less than nb. Now we divide by n, and n is positive, so we'll get a less than m by n less than b. So we see that m by n is a rational number lying between a and b. So first part is done. Here we can use the density property of rationals to get the required result. Otherwise, independently we show the rest part. So for we suppose that r equal to m by n. Now a less than r less than b. So now if we consider two numbers r and b, so in between r and b we'll get another rational number which is named as r1. So we have a less than r R less than R1 and R1 less than B. Now R1 and R2 are two rational numbers, so their arithmetic mean is also a rational number, and we know that R plus R1 by 2 will lie between R and R1. So on this line, R plus R1 by 2 will be in between R and R1. Now we use the same technique. Now we consider the number R and R plus 1 by R2. So this one and this one. So proceeding as above, we find that between R and R plus R1 by 2 there exists another rational number, and this one is this. So R plus R1 by 2 divided by 2, and this will lie between R and this one, and this is less than R1 from there. Now simple calculation will get from this inequalities to this one. Now again, if we consider the two rational numbers R and this one, so between these two we will get another rational number. So this one, its position will be here, and this number is this one, and this one will be lying between this and this, that means R and this number. Okay, now after calculation, if we add R and this one, so we'll get this one. So we proceed similarly, and we recall that arithmetic mean of two rational numbers is also a rational number, and we proceed as above to get that R is less than 1 plus 2 plus 2 square plus up to 2 to the power n times R, your outside is R, plus R1 by 2 to the power n plus 1, because here there are three numbers, so its power is 3. Otherwise it ends with power 2, so it will be increased by 1. So here ends with n, so its power is increased by 1, so it's n plus 1. Similarly 1 plus 2 plus 2 square after 2 to the power n minus 1, it is increased by 1, so you'll get n, etc. So we find that if we increase the values of n, we will get infinitely many rational numbers in between R and R1. So between any two rationals there exists infinitely many rationals, and these are all in open interval AB, because whenever there exist infinitely many rational numbers between R and R1, they are also in the open interval A and B. That's all.